raindrop falls at a certain constant vertical velocity of 1.8 meters per second in still air. The mass of the drop is 7.2 times 10 to the power minus 9 kg. So what is the work done on the raindrop by gravity as it falls through a vertical distance of 4.5 meters? So let's start with drawing a simple diagram of the forces acting on the raindrop. In the vertical, we have the weight and the drag forces. Given that the raindrop is falling at a constant velocity, so the net force on the raindrop is 0. Both the weight and drag forces are equal in magnitude but opposite in direction. The work done by gravity, just use the formula for work done, F times displacement times cosine theta. In this case here, theta is 0 since the displacement and the force of gravity is in the same direction. So the answer is 3.2 times 10 to the power minus 7 joules A. Next question. How much work is required to accelerate a 1000 kg car from 20 meters per second to 30 meters per second? Draw a simple diagram again. The initial speed is 20 meters per second. The force that is on the car is the driving force of the engine. And at the end of the acceleration, its final speed is 30 meters per second. Use the work energy equation. The work done by the driving force of the engine is equal to the change in the kinetic energy of the car. Change in kinetic energy, we take the final minus the initial. The value is 2.5 times 10 to the power 5 joules. Answer D. Question 3. A bicycle dynamo is started at time 0. The graph shows the total energy transformed by the dynamo during the first 5 seconds. At which portion of the graph will you have the maximum power generated? The gradient of the energy versus time graph is the power of the bicycle dynamo at that instant. By visual inspection, we can see that the maximum gradient will occur between the time t equals to 2 and t equals to 3 seconds. The gradient between 2 and 3 seconds, 0.4 minus 0.1 divided by 1 second, so answer is 0.3 watts. Answer C. A force of 1000 newtons is needed to lift the hook of a crane at a steady velocity. After that, the crane is used to lift a load of 1000 kg at a velocity of 0.5 meters per second. How much of the power developed by the motor of the crane is used in lifting the hook and the load? Let's quickly also draw a simple diagram. Given that the motor exerts a force of 1000 Newton to lift the hook steady speed, then using Newton's second law, we can deduce that the weight of the hook is also 1000 newtons. The total weight of the hook and the load is 1000 newtons for the hook, and then the load is 1000 times 9.81, so making a total of 10,810 newtons. The power developed by the motor will be used to lift the load and the hook. The formula is F times velocity, so it's just 10,810 times 0.5, so it's 5405 watts. Answer D. Question 5. A ball of mass m 2.6 kg falls from rest, falls a vertical distance of 55 cm before striking a vertical coil spring, which then compresses by an amount y equals to 15 cm. You need to determine the spring stiffness constant K of the spring. You assume that the spring has negligible mass and ignore air resistance. We show here the situation. Initially, the ball is at A, the height of h from the spring. The reference level, we take it as the uncompressed length of the spring, and after the ball comes to rest, the spring is compressed by y, which is 15 cm. That is the final state, B. We use the principle of conservation of energy. No work is done on the system, or no work also lost by the system. And we take the reference level as the top of the coil spring, and we let K as the stiffness constant of the spring. Energy at the point A is equal to energy at point B. We consider all the energies at point A, which consists of the gravitational potential energy, kinetic energy, and elastic potential energy of the spring. This will be equal to the energy at point B, which also consists of the gravitational potential energy, kinetic energy, and the elastic potential energy. Substituting in the values, at point A, there is no Ke and no elastic potential energy. At point B, there is gravitational potential energy, but since we consider the reference level as that of the spring, the height is a negative 0.15. We assume that the ball has come to rest at the final compression, so there's no kinetic energy, and at point B, the spring has maximum elastic potential energy. Solving for the value of K, you have K equals to 1590 newtons per meter. A driving force of 200 newtons needed for a car of mass 800 kg to travel along a level road at a constant speed of 20 meters per second. Then what power is required to maintain the car at this speed when it goes up a slope where the car rises 1 meter for every 8 meter of travel along the road. When the car is on the level road, the forces acting on the car is the driving force of the car and the resistive force on the car R. So from Newton's second law, given that the car is moving at constant speed, the net force is 0. So the resistive force R is equal to the driving force Fe of the engine, 200 newtons. The gradient of the slope is 1 meter for each meter, so that says that the sine theta of the slope is equal to 1 over 8. If we draw the forces acting on the car on the slope, the difference between the case on the level road is that now we have a component of the weight of the car acting along the slope. So if we resolve the forces along the slope, and noting that the net force is still 0 since we want to have a constant speed, then F, the force of the engine, and the resistive force and the component of the weight along the slope must be equal to 0. Solving that, we can determine that the force exerted by the engine will be equals to 1180 newtons. Power exerted by the car engine equals to force of the engine multiplied by velocity. So the answer is 23600 watts.